Ions and ionic bonds. We have been discussing the structure of the atom and the structure of the periodic table. We will now begin to see how atomic structure relates to the formation of compounds by the formation of chemical bonds. We will begin by looking at ions and how they are formed, which then leads to the formation of ionic bonds. But first, recall the structure of the periodic table. Elements in the same vertical column, or group, all have the same number of valence electrons. Valence electrons are the electrons in the highest number main shell. All the other electrons in an atom are called inner electrons. So the first group, on the far left, all have one valence electron in an s subshell. The next group over all have two valence electrons. Then, moving over to the p block, the third main group has three valence electrons, and it goes up from there. There are a couple of different conventions, unfortunately, for numbering the groups, depending on whether the one numbering the table is American or European. But the numbering convention which will be the most useful for us is the way it is shown here. This is also one of two ways the large table in the classroom is numbered. Note, I have not labeled the D block groups. We will not be using the transition elements much this semester. Using this numbering scheme, the Roman numeral over the group also tells you the number of valence electrons in that group. We are counting all the electrons in the outermost main shell. It doesn't matter at this point what subshell they are in. So, for example, group 4A has 4 valence electrons. Group 6A has 6 valence electrons, etc. Now recall that group 8 on the far right of the table is the noble gases. These elements are very stable and unreactive. They all have 8 valence electrons, full s and p subshells, with the exception of helium. And since helium is so small, it only has the one main shell, which can only hold 2 electrons. So mostly we're talking about the remainder of the noble gases here. Now look at a chlorine atom. Chlorine is in group 7A. It has 7 valence electrons. Our stable number is 8. If chlorine could just find one more electron from somewhere, it would have 8 valence electrons, the stable number. This is indeed what happens. In order to be stable, chlorine will gain 1 electron to have full s and p subshells, a stable configuration. So the electron configuration then looks like argon's electron configuration. Argon is one of our noble gases. But chlorine is still chlorine. We haven't changed the nucleus. It has 17 protons. So after gaining an electron, it now has 18 electrons. The number of electrons is not equal to the number of protons. The atom now has a negative charge. It is an ion, an anion. Simple anions, made from a single atom, are named by dropping the last syllable or two from the element name and adding the suffix IDE, ide. So we now have chloride ion, a negatively charged atom. Let's now look at an element from the opposite side of the table, group 1. Sodium has 1 valence electron. If it were to gain electrons until its valence shell was stable, it would need to gain 7 electrons. 7 is a lot, too many extra for the nucleus to hold on to. So instead of gaining a bunch of electrons, sodium will give up its 1 valence electron. Now it has an empty valence shell, or the next lower shell is now the valence shell, and it has 8 electrons. Stable. It looks like neon, another of our noble gases. But once again, we haven't changed the nucleus. There are still 11 protons, but now there are only 10 electrons. We have a positive ion, a cation. Simple cations are named simply by the name of the element with the word ion after it, sodium ion. So atoms will gain or give up electrons in order to have stable electron configurations, full S&P subshells, like those of the noble gases. 8 valence electrons is stable. Atoms form ions to get to 8 valence electrons. But electrons don't just disappear or come from nowhere. They are very small, but they are still subject to the law of conservation of matter. So when sodium loses an electron to form sodium ion, that electron must go somewhere. If there is nowhere for it to go, it remains as sodium. Likewise, chlorine atoms must have a source of electrons in order for them to form ions. If there are no electrons available, chlorine stays as chlorine. But if sodium and chlorine are mixed, sodium can give up its 1 valence electron to chlorine, filling chlorine's valence shell to 8. The sodium ion and chloride ion are then attracted to each other because of their opposite charges, forming an ionic bond, the attraction between oppositely charged ions. The formula for an ionic compound is written by putting the symbol for the element which forms the positive ion first, then the symbol for the element that forms the negative ion. The charges on the ion are not shown in the formula for the compound. It's just written NaCl. The compound is named by saying the name of the positive element and then the name of the negative ion, sodium chloride. In order to have a neutral compound, the charges on the positive and negative ions must balance out. Gaining or losing electrons makes a huge difference in properties. Sodium is a soft, highly reactive metal that reacts violently with water, and many other things. Chlorine is a greenish, toxic gas. It was used as a war gas during World War II. If you mix the two together, a violent reaction occurs, and the product is sodium chloride, table salt, used as a flavoring and preservative in food. You probably eat some every day. Ionic compounds tend to form crystals, structures of alternating positive and negative charges. Crystals are generally hard and have very high melting points. In class, you will get a chance to practice figuring out ions and what compounds are formed from the combination of ions.